Welcome Neal, and he will be introducing our panel.
So before we get started, I want to introduce our panelists. First, I'm going to introduce Dr. Sung Park. Sung is the Senior Engineer for Manufacturing and Materials at Northrop Grumman Aerospace Systems. He currently leads high-temperature metallic additive manufacturing for Northrop Grumman Aerospace Systems Advanced Materials and Processing Development Group, with work that covers feasibility of metallic AM components on a whole host of systems. He also supports Penn State's Open Protocol for Powder Bed Additive Manufacturing America Makes project and is currently managing DARPA's Open Manufacturing Transition Study for metallic AM parts for air vehicles. Next, I'm going to introduce Richard Martikanitz. Dr. Martikanitz is a division head of laser processing of the Applied Research Laboratory at Penn State, as well as the director of the University Center for Innovative Materials Processing through Direct Digital Deposition, or SIMP3D. He serves as the program manager for SIMP3D Penn State's activities under the DARPA Open Manufacturing Program, and his primary interests are the impact of process reliability and its effects on product performance on additive manufacturing. He has over 35 years of experience in materials manufacturing, so he must have started this quite young. And finally, rounding out the panel is Mark Benedict. Dr. Benedict is a senior materials engineer for the Materials and Manufacturing Directorate at the U.S. Air Force Research Laboratory. He is America Makes Chief Technology Officer. He's also a major leader in the AFRL Mantech community. He's currently leading many large and novel data science and AM programs in the areas of additive manufacturing, variability assessment, AM qualification, and in situ sensing for additive manufacturing. So that's our panel. What I wanted to talk a little bit about was, well, first, before I introduce these slides, let me explain the source of the slides. So I'm channeling my inner Mick Marv. You heard Mick Marv yesterday, I believe. These are not my slides. These are Mick's slides. It's just, there's only so many times you can hear from Mick. So I'm going to channel my sardonic former bureaucrat and do my best here. What we're going to talk about right now is the challenges for qualifying aerospace and defense additive manufactured parts. And I love this slide. This is sort of a typical Mick Marv slide where you're saying, not so fast. So, you know, there's a reason why I'm not in PR for 3D systems, right? Because I want to first say there is great promise, and as we've said, there are some parts that are being integrated into the aerospace and defense supply chain, and it takes a heck of a lot of work to make sure we meet those qualification certification standards. So what's nice about these slides is, on one hand, we have the promise. And it's real. The promise is real. Greater component design flexibility, lower buy-to-fly ratio, improved time and efficiency capability. But the challenge is also quite real. That's a shameless plug. That's a ProX320 3D Systems product. So the current manufacturing environment does not capture process data. We have poor understanding still and a control of materials, machines, and processes, although there are phenomenal companies like 3D Systems that are trying to get their handles on it in partnership with key folks here up on stage. And then, of course, the make or break qualification approach is too costly. We need to figure out how to transition AM to the market, but it requires overcoming significant qualification challenges. And we're going to leave this slide up on stage to sort of, or up here to sort of talk through the issues that we want to address today with these folks. This kind of illustrates, again, the source is DARPA. This sort of illustrates the considerable amount of money and the considerable amount of time that it takes to qualify and certify additively manufactured, well, any part, any material, and any process into the system. It requires a comprehensive understanding of manufacturing variation at different scales. And this can take upwards of 15 years, and as you can see, millions and millions of dollars. So with that preface, I'd like to have the different panelists discuss their perspective on overcoming these challenges, and perhaps, because we're all kind of hoping we can start cashing in and getting the revenue and realizing the promise, perhaps figure out ways to short circuit this a little bit and encourage the Air Force and big system integrators like Northrop Grumman to buy our machines already and start making parts. So with that, I'm going to ask first for industry to provide their perspective and have Sung talk from Northrop's perspective, and then have Mark provide his insights as to why the Air Force's approach, or how the Air Force is approaching this problem. I shouldn't compare services, that would be dangerous. And then finally, have Rich provide his perspective from his position at Sim3D. So Sung, do you want to start it off?
Sure, thank you. If you look at that chart, I mean, there's unfortunately underneath the coupon that you start making coupons and generate the material properties once you fully understand the process. There's no meaning of generating a bunch of data when you cannot guarantee a consistent data coming out of the process. I mean, currently metallic AEM process is very, similar to early days of composite manufacturing. Composite properties depend on both materials and process. That's why you tightly control the materials and process specification, right? So we spent a lot of, in earlier days, to understand the process of composite manufacturing, to fully understand the process and reduce the variability arise from the process. So once you lock that down, then you start generating the data by making coupons, et cetera. So what after you generate all this data, basically you publish a design allowables. That's what the designers will use that data to design the part, and then that is accepted by your customer. That when you have that design allowable, they're going to say, okay, you pretty much guarantee that properties based on the documentation. So there's traceability from the design allowable all the way down to the materials and process for the composites. For additive manufacturing, it's very similar to composite. The properties depends on both materials and process. But there's another added degree of difficulty is that now the performance also depends on the geometry or build layout of the parts. And not only that, we don't fully understand the process yet, or if we don't have fully control of the process. There's a many variability, there's a many uncertainties arise from the process. So question is, forget about building all these coupons, et cetera. I mean, how are we going to manage those uncertainties and variability arise from the process? And that kind of dictates, whether you can transition the parts to the platform. I mean, as an industry, we fully understand the benefit of AEM, and we want to transition the part. Always the problem is, there's a detailed level of, the pedigree, the traceability of the data you are generating is applicable to what you're going to design to. So there's a lot of still questions regarding, okay, we have witness coupons while you're building your part. But there's a question, does witness coupon really reflect the properties of the actual part? That's a big question. And also there's now robust inspection method. Even CT scan will not guarantee you the defect-free zone for some flight critical components, for example. So having all that throw into that, a certification and qualification arena, it becomes very, very difficult. So as an industry, we don't want to spend a whole lot of money in terms of generating data unless we fully understand the process, unless we are fully comfortable and we have a way to manage that risk. And that's one thing. And also, we have to look at a different approach, meaning that one qualification certification price will not going to fit everything. I mean, there's some certain applications, for example, electronics division, they don't need to go through all this hurdles to transition their part, right? So we have to look at the program-specific, application-specific, and also some type of zoning approach may be applicable. For example, casting uses has the similar problem in terms of control of the uncertainties arising from the process. So they put casting factor in it. Is it, easy way out for the AM is put some kind of AM factor in it, but that kind of defeats the purpose of maximizing the benefit of AM. So we try to not to do that. But certainly, certain application will dictate how the part will be certified and qualified. And we have to be cautious and prudent in a way that, what part really is suitable for AM process, as well as the chance of success of getting certified.
So, Mark, so that means no one-size-fits-all approach here? What's the Air Force's perspective?
Well, so I'm going to address this from two different perspectives. As the Chief Technology Officer of America Makes, we're supporting qualification for additive manufacturing by forming, convening the industry, the U.S. industrial additive manufacturing base, to identify best practices and then try and normalize those across the industry. So I'll give you two examples of that. First is in situ sensing. We've got a lot of investments there. Many people are researching this area. We all think it's promising, but little concrete evidence has been presented on positive return of investment in that technology to date. So we're trying to work in this pre-competitive environment to identify, really what aspects of in situ sensing are going to deliver the most return on investment. And we think that is a critical element of qualification. The second example is the America Makes Standards Collaborative. So this is a collaboration with ANSI to essentially create an additive manufacturing standards roadmap and gap analysis and support the over 19 different standards development organizations in starting the process of writing the specs that we critically need to really, again, normalize that vendor base in the additive industry. So that's the America Makes role. I also spend about half my time supporting Air Force qualification efforts directly. And I'd say we have a 4-tier qualification strategy, really. And the first is to get experience with non-certified components. So that's tooling, fixtures, ground support equipment. Really learn a lot of our lessons there in a very safe environment. The second tier is where we're at now, and really where we've been since about 2004, and that's point design. So qualify individual parts where the geometry is part of the critical parameters, as well as pretty much everything around the process being completely specified and frozen. So this is not a very flexible approach. It's not a very affordable approach, but it can lead to safe parts that are currently flying today. We have some on the F-15 as an example. Where we want to go next, Tier 3, is part family design. So to get there, to get qualification working in that environment, you really have to essentially identify what the essential process variables are. With the powder bed additive process as an example, depending who you ask, there's anywhere from about 150 to 250 essential process variables that have to be specified and controlled. And then eventually we'd like to get to Tier 4, and that's rapid qualification, qualification of lot size of 1. That's going to take a lot of effort from where we're at now. Certainly high fidelity validated models are going to be a requisite component, as well as kind of understanding all of what we call inside the bed physics of the powder additive manufacturing process as an example. So that's effects of defects, defect distributions, critical initial flaw sizes given those effects of defects. A lot of the very challenging things that we don't have good data on currently.
Rich, what's your point of view?
Well, I start out and agree with everything that certainly Mark and Sang had mentioned earlier. I would like to give you by prefacing my introduction with a very short description of our center, which is the Center for Innovative Materials Processing through Direct Digital Deposition at Penn State. It's a very large research facility dedicated to the advancement, demonstration, and dissemination of additive manufacturing technology. We do about $10 million of research per year in additive manufacturing. I'd like to also add that I think we have a unique perspective from a qualification standpoint. Our organization has qualified two processes in the past for additive manufacturing. These two cases, which were related for repair for the U.S. Navy, that's being used and has been used for over a decade now. We also recently partnered with the NAVAIR Systems Command as part of their strategic team in doing a point design, point qualification for demonstration of components for the V-22 rotorcraft. And we were very instrumental in supporting and assisting in that process. So we do have some experience in being able to develop at least point qualification protocols. In fact, we developed about 3 years ago a very simple means looking at performance qualification as your central point for qualifying the process. And that entailed really three entities. One being your incoming material qualification, two, your system. When I say system now, I'm talking about the manufacturing, additive manufacturing system itself, qualifying that to ensure performance and reliability. And then finally, a performance qualification based on the unique requirements for that particular application. Performance qualification has been around for many, many years, actually for over 70 years. That type of approach has been used to qualify a process and performance requirements for various applications. So we think that is one approach. It's a very time-consuming and costly approach. It's not akin to what we've shown with the pyramid. It is costly and time-consuming. So how do we accelerate that type of process or compress the time required to get to now qualification of family of parts or commonality amongst processes and parts and materials? So we think there's really three important categories in that regard, and it just so happens that a lot of our research within our center is directed at that. And certainly we need to have, in our opinion, an improved understanding of the process as it relates to the microstructures that are produced, the post-processing requirements needed to fulfill the performance requirements for that process or product, as well as the machine interactions with the material. We think that's very important. That has to be based on very sound scientific and engineering principles. We can't base our understanding based on observations, anecdotal evidence, or personal beliefs, and that's what I occasionally see quite often. Frankly, I saw some of that here during the conference, and I'm sort of dismayed. I think we need to back up our understanding with sound engineering principles supported by strong data, and we're very deeply involved in all aspects of improving our understanding. Secondly, we should be able to bring to bear some of the modeling and simulation techniques that we believe the U.S. has a strategic advantage in, and we should bring those technologies to bear to not only help us improve our understanding of the process, but to provide a greater quantification to the interaction between the process and the material. That becomes important in many instances that when we freeze a design, freeze the process, and go through a performance qualification, we have essentially one point that we're defining within this entire regime. Through the use of simulation techniques, and this isn't necessarily all numerically and intensively computational. These can be very fast analytical approaches, but simulation techniques allow us to explore a broad range of processing conditions, now allow us to bound our process window. And if we can bound our process window, then we can look at sensitivity of some of our important parameters. If we can have that information, that gives us insight into potentially reliability and its inverse uncertainty of the process. So that's important, simulation capabilities. And then finally, I think in the area of sensing, I'm going to preface that by saying two levels. One is in very simple capabilities today that we have for now monitoring are essential or primary variables. So that ensures that we have a documentation of the pedigree of the material that we're producing, or a quality assurance record, and that is something that we need to insist upon today from our machine producers, to be able to have all of that information concisely available during that process that we can then archive as a document record. And that's should be available today. And then we can get into then more future benefits, such as advanced sensing technologies that's going to allow us to now measure and define the reliability of the process as we are processing, and potentially take some type of intervention, be it direct machine intervention or manual intervention during the process to again ensure reliability. So that's pretty much my perspective.
So how do we square, I guess, what Rich and Mark are describing with what Sung is saying, which is basically, God, we have so much liability here. We don't care. 3D Systems could be selling you a machine and swearing to you that it's going to work, but and then we can produce some documentation that we've been working with Rich on some process. But how do we validate these models? How do we validate the data? I guess there's sort of this strange dichotomy where you have what Sung described as being, sort of tethered in practical reality, and then some of these other projects that seem like they should work, but we haven't yet validated that. Is there a discrepancy here, or is there a work underway to move in the direction of the vision that Rich and Mark described?
I mean, for industrial point of view, that's where we want to go, right? There's 100% digitalizing the entire, from the modeling of the part, manufacturing, inspection of the part, and final product coming out of AM. That's our ultimate goal. If you have a perfect system of modeling, in situ modeling process, inspection method, I mean, by the end of AM production, you basically have a qualified part. You don't really have to go through other unnecessary inspections that follows after a typical, composite manufacturing type.
So you're willing to toss out the pyramid that we.
But however, I mean, that's the ultimate goal, but we're not there. It's going to take a long time if you're going to wait for that to happen. So, I mean, we have to look at what can we live with in terms of the risk. It's all about, I think, is risk management. Certain applications and certain programs are willing to accept higher risk. For example, we just released a process material specification for the Type 64 for EBM process for space application. For space applications, every flight critical components go through a proof load test. Basically, it's point qualification, point design process, point qualification. So it doesn't matter for them, really. They can accept the risk you got from the current, variability that arises from the AM process. With enough data they've seen and analyzed, they agree that they can accept the risk they have with the current system. And with the addition of the proof load testing, other inspection method, they're confident enough that we can transition that now, right? And also, it has to do with the life cycle of the part, right? For satellite business, you're talking about surviving the launch load. After that, who cares? Yeah. But air vehicles, you're talking about years of service life, right? So that comes into play for the fatigue life and et cetera. So that adds the degree of difficulty in terms of inspecting the part that will last 20, 30 years, right? So again, we have to look at a program and application and see what we can accept and what we cannot, and go from there. Again, one part that transition to any platform is good for our industry and AM industry, right? So we're going to build that successful story and continue make progress on what Rich was saying about regarding the monitoring capability, modeling capability, controlling of the AM process in general. So ultimately, hopefully we'll get there, that we don't have to do all this unnecessary.
So I'd like to amplify what Sung said, in that the space industry is leading adoption of end-use additive parts, and I think that's a good thing. You know, there's standard practice of proof testing, so functional testing requirements defined for the components. The designs are very static compared to other industries. So, you know, the rocket engines we're using today are 40-year-old designs by and large. They're well understood. So you have a lot of stability there to proceed from. And I think, you know, hopefully in the next month or two, we're going to have some success stories released for some large programs that we've been investing in, where they've been, you know, testing the components and seeing, you know, absolutely great performance and order of magnitude cost decreases in the component and really rapid reductions in cycle time for producing the components. So I think that those successes are likely to help enable the qualification of the, you know, the long life components, the 25,000 to 50,000 hours we need out of an aircraft component, for instance. You know, I think those space successes will help transfer, you know, hey, if we're making those gains here, what can we do in this other space?
So we're using technology, by and large, that's 15 years old, right? I mean, the powder bed laser fusion system, it's innovative. There are a lot of great incremental innovations that have been made along the line, but by and large, the principles are relatively old. And even as we talk about condensing, as you were calling it, the qualification cycle, there's still concern, of course, that we're going to lock in a particular technology, a particular kind of machine, and we're not going to be able to continually innovate. So how can a equipment manufacturer live with themselves? We want to continually push the envelope, continually innovate, and it sounds like the goal here is to test considerably what the properties are going to be for any particular application, and then lock in a machine. Is there a way to strike a balance to embrace innovation, embrace upgrades to technology? What are these kinds of innovations that you're seeing on the market today, Mark or Sung or Rich? What are the kinds of innovations that we'd like to see brought to the manufacturing and are there ways we can figure out how to qualify those new technologies or have that kind of spiral development take place?
For industry perspective, it's not much of innovation, but we'd like to see from the machine OEMs more openness in terms of, you know, their process conditions or process parameters, because a lot of time it's a black box, and each company has their own way to scan a laser path, and they're not going to release that information, right? So for us, try to understand fully a process before you can even make any coupons. That's a big risk, right? We cannot deal with unknown and then generate the data and then build upon that, right? Because what happens if that change that parameters, so let's say even optimize the parameters, as you constantly see these days. And that's always challenging, you know, when you deal with machine OEMs, is that first, you know, their own proprietary nature of how they make the part or how they control the process. Another thing is like, you know, okay, you have pretty good understanding of that, and you try to invest time and money to generate some data, and then all of a sudden, oh, we have an even better process, you know, scheme that it will give you a better result. So all the money you spend and time you spend may not traceable to what they're going to do, right? So there's some risk of that associated with it. So I don't know whether it's you know, it makes sense for the business, for the machine OEM like you guys, but I'd like to see some more openness in terms of, you know, providing the fundamental process parameters.
Yeah, I'd like to follow up, and I agree totally with you, Song. For the most part, if we look at powder bed fusion, these systems are very similar in the basic principle of their operation and the process itself. There should be the ability to transfer parameters from one machine to another machine so that we can then define the very critical or important parameters, and with that we should be able to reproduce then parameters amongst machines. You know, there's an analogy here. If you go out and buy 6061 T6 material from various suppliers, you have an assurance that the properties that you're going to expect will meet some defined limit that is controlled by the manufacturing processes that the various suppliers use to achieve that goal. We need to be in that situation from a processing standpoint regarding the equipment itself. And so transferability of process parameters from machine A to machine B becomes, I think, extremely important in being able to broaden then our supply chain for potential applications.
So I would say that, Sung really hit it when, open systems are critical to allowing new technology to enter the industry without destabilizing the qualification process. But I would like to say that in addition to that, maybe the very next most important thing that the machine OEM should be embracing is the modeling and simulation capabilities. Because I really think support for those will build industry confidence in new capabilities as they come online. So whether that's through the open architectures and information to scan paths and parameters, or extensive characterization capabilities within the machine, or a lot of co-funding of material property characterization. Again, I think it's the models and simulations that will really keep us from getting too locked into the current generation of hardware.
From the audience, we have a couple of questions. The first one is, the industry tends to work with commercially available AM materials. And I would we don't even have to say AM materials. Maybe we should just say the industry tends to work with commercially available materials. Do you think we need to look at MRL 1 through 3 materials development, and I would say specifically tailored to the additive manufacturing process? Rich, do you want to?
I certainly agree with that. The materials that we're using today, for the most part, were developed for wrought processing techniques that's very based on thermomechanical processing that allow them to develop the microstructures and the resultant properties that they can achieve. There are vast differences between that sequence of processing versus a rapid solidification process that we achieve with additive manufacturing. So why not take advantage of the very high cooling rates and solidification rates that we achieve to develop very unique properties and materials? Yes.
Do you want to say anything else about it?
Well, so additive manufacturing alloys or plastics, depending what your interest is, certainly have a lot of potential. I'd say it's in the TRL 1 to 3 space. So America Makes and Air Force Mantech has challenges engaging at that level, but we do collaborate with other institutions and consortia that are active in that area. I think there are gains to be made. We've certainly had a lot of feedback that there is desire to do that kind of research, but it is a long-term process to develop new alloys, very long. Yep. And the IP concerns get pretty challenging for teams, particularly. Absolutely. I think. So it's a very challenging space to work in for factors beyond just the pure utility of the solution.
Well, right, and Sung, I mean, I would assume this gets back to your earlier comments, which is, look, you know what TIE 6.4 is supposed to look like, and now we're talking about possibly, as an example, maybe developing some sort of boutique additive to make TIE 6.4, as an example, or some other alloy optimized for a machine. It might produce great results after the fact, but that would create additional headaches, I guess, for you as part of the qualification process.
No, I think the basic, understanding is that, basic chemistry composition remains the same. Right? Yeah. You cannot really call TIE 6.4 and then your optimized powder is not really TIE 6.4, right? So, I mean, that's the understanding of that, basic chemistry of the powder remains the same. But, if that AM optimized powders will help the, reduce the variability that arises from the process or reduce the defects per se.
Lower distortion.
Absolutely. Then, that's great. I don't see why can be happening.
It's one thing to mention, I think, when you look at that pyramid from a process qualification standpoint, there's only one other thing that's longer than that, and that's a material qualification. So that's going to have challenges in itself as well, Neal.
So I'll add one more point to that, and we've seen this several times in the industry. No material spec is so locked down that there isn't wiggle room within that spec. So knowledgeable vendors have found the sweet spot for Inconel 625. Slight change to this element, slight change to that element, but within spec, and then they order powder to their tightened spec. We've seen fairly positive improvements in that space, and it doesn't really challenge that whole the current qualification structure. So it is materials development, but it's almost materials refinement.
I think another good example of what you just said, Mark, and I totally agree, that may be our transition from new materials to refinement of existing materials, and our precipitation strengthened stainless steel alloy 17-4, I think is a great example. You can have a composition that is pretty close to being identical, but depending upon the way in which it was atomized can affect its ability to respond to heat treatment significantly, which I think a lot of people that are involved in the industry is aware of. So now people are now addressing the atomization process and literally now refining the processing and to some degree chemistry of powders for additive related to that family of materials.
Another question is, yesterday, several panelists indicated that additive manufacturing could not compete with conventional machining. Do you agree? Why or why not? And I might add, perhaps,
Sounds like
maybe there's a, maybe there's another way to characterize it. Maybe there's a way to suggest that additive may just be one tool in the toolkit. And where do you see additive playing versus some of the other conventional processes?
Well, I mean, obviously you don't want to make a simple geometry out of AM. You're never going to beat any machining in that cases, and there's no reason to do that. You only selected part that you absolutely cannot make the design without any additive manufacturing process. That kind of makes sense. Or very complex design that is cost prohibitive to do some traditional machining, etc. Right? So again, AM cannot apply to every single product out there. It doesn't make sense. We have to be prudent, in terms of selecting what type of part that you want to make out of AM, and that includes both the geometry, the cost of lead time, cost of weight saving, etc. Everything has to be, in trace study in a way that it has to make sense. So I'm not sure, that's the right statement. It depends on what part you select to make the AM, and certain parts you just cannot make with the traditional method. So how do you compare that against AM?
So in my official capacity for manufacturing technology, my response is required to be, if there's any other way to make it besides additive, please do that. We understand those processes. They're generally going to be at a cost advantage. But I think there's some major caveats to that, and I'll relay one experience that I've had. In a program where I was looking at we were asking to replace aluminum ducts with additive printed thermoplastic ducts, we were said, yes, we can see some advantage to doing that. But your duct has to meet all the materials property requirements of the original aluminum duct, and you're really not allowed to change anything. And so immediately, if you don't design for additive manufacturing, if you're trying to drop in replacements to things that have been optimized for conventional manufacturing processes, you're at such a huge disadvantage that it is often not sensible to pursue additive unless diminished source considerations is a major factor. So really the desire to use additive and the real cost benefits are going to come when you're allowed to design for additive, and whether that's part consolidation or creating functionality that just can't exist without additive. And I'm particularly thinking of components like heat exchangers and parts that need large degrees of cooling in the power industry. additive is a game changer there. So cost isn't the issue.
Sweet. You play a very critical role in America Makes. In fact, all the folks up here on stage play key roles in America Makes. Can you comment a little bit about where you see the future of America Makes? You clearly define the role in terms of the TRL scale, 3 or 4 to 7. So there's a role, there's a function here. What does the future hold for that institute, as well as all the other government programs that are being developed? Is the Air Force and are your institutions dedicated to supporting not necessarily the institutes themselves, but the notion of collaborative research and development and moving forward with this model?
So as I stated, my vision of the prime focus for America Makes is really acting as that convening body for that pre-competitive consensus forming and technical matters in the additive manufacturing industry. Now, it's a national manufacturing innovation institute, that was stood up about 4.5 years ago. So we're almost into our 5th year, which was in the original continuing agreement, the contract between the government and the private entity, NCDMM, that runs America Makes. That expires in year 5, and then we move on to the second continuing agreement, which is in place. And the thought is that the innovation institutes transition from publicly supported institutions in the first 5 years to public-private partnerships in the out years. And so that's the phase that we're looking at. And really what that entails is a lot more participation from the consortium members in terms of co-funding and driving the projects that we select to work as the battlegrounds for forming that pre-competitive consensus. And I think there will be more direct agency involvement. So, the different departments within, different agencies within the DoD and the different departments across the government, DOE, Commerce, participation from those entities in moving forward the qualification of additive manufacturing, I think, is really where America Makes is heading in the next 5 years. But we have had some, obviously had a large transition in the recent past in our political infrastructure, and the signs initially are quite positive for the manufacturing institutes and the support therein. But we're developing what that's going to look like rapidly, let's just say.
Do you want to add anything? Or?
I think it's great for a program like America Makes. This is good for establishing the foundation of the AM process in general, solving those tough problems. Only difficulty for private industry, with the government, is that program is structured in a way it's cost share and then IP share. So I always have to justify to my management whenever we're going to go bid America Makes proposal, et cetera, why we're doing this, right? Why we spend our money and then we don't really claim your IP, right? So that's some philosophical, I guess the difference in terms of how management views a funding mechanism like America Makes versus the technical engineers, where we just want to solve the problem, wants to get involved with America Makes.
I would like to put a plug in for America Makes, as well as our center at Penn State. 2 years ago in the fall, along with partnership with America Makes, we convened a meeting to look at coordination of U.S. standards. Everything we're talking about has to be supported by a strong infrastructure of standards that allow us to take these types of qualification protocol forward. Standards are key. And we convened at that point. America Makes literally took the bull by the horns, identified and teamed very closely with ANSI, which has as their charter and mission the coordination of standards in the U.S. And since then, they've been developing a very detailed roadmap defining, as Mark pointed out, the requirements as well as gaps that we need to have a cohesive selection and portfolio of standards within the U.S. that will support all these things that we're talking about concerning qualification. So they've done a marvelous job, and I don't think anyone could have pulled that pulled that out except for America Makes and certainly ANSI.
So this was already addressed. We're running a little bit out of time, but I guess we can reiterate this question because I think the other services are looking at this more maybe than the Air Force. But the question was, what about using AM to monitor supply chain just in time, et cetera? Is that a good use? So I assume this is, again, sort of addressing this question of using it in a logistics capacity to replace parts that were made conventionally.
So the biggest challenge we have right now with regards to logistics and additive manufacturing is the digital thread. So additive manufacturing is a massively data-rich process, and we have to identify, what elements of the data that we generate in that process do we keep. But conventional practice has been, we don't own the technical baseline. We, the Air Force, we, the Navy, we, the Army. We need to move more in that direction and essentially keep the required data to recreate parts in from one vendor to the next, which really does not exist. We have some large programs that America makes that are looking at sustainment in the aerospace context, and it's a challenge to find parts that we have sufficient requirements data about to recreate those parts in an additive context. And the reason we need to recreate those parts is because the original vendors went out of business long ago. Some of the platforms like the B-52 we've been flying since the 60s, or early 60s, I should say, maybe late 50s. The vendors are long out of business, so replacing critical parts for that kind of aircraft is the biggest problem we face. I think it's a little overhyped that we're going to deploy printers in forward locations and create quality products. I don't think we're anywhere near that. I don't want the warfighter using inferior quality products that don't have proper quality control on them, except for limited use.
It'll all be automated,
Yeah.
robots.
Yeah. So recovery of aircraft, get it home kind of operations, not to print anything at a forward location and use it for length of mission.
But Penn State recently printed parts for NAVAIR, and they've flown successfely on a rotorcraft. Is that right, Rich?
That was the V-22 sustainment activities that we're continuing to be very deeply involved with NAVAIR. But that was a very point design. It was an existing design. We were replacing essentially components of the nacelle that were fairly simple, not flight critical, but important components. And there was quite a lot of effort in the detailed definition of the process, establishment of expected properties, which included not only the manufacturing process, but post-processing. Everything was 100% hipped. Everything was all surfaces were 100% machined. So it was, risk mitigation was built into the program, and we were quite successful in being able to do that. You can't afford to put forth that much effort for every application. So we need to find ways to compress some of these considerations.
Absolutely. Great. Well, the Academy Awards music is starting to play, so please give these folks a round of applause. Thanks so much for your time.